This is Mr. Collier, and today we're using the second derivative test to sketch functions. Okay, here we have a function, and some interesting points are along these dashed red lines. I'm just going to add one more because there's one missing. Something interesting also happens along here. Okay, I'll try to draw that as straight as possible. Alright, so if we take a look at this function, we have right here we have a maximum, and over here we have what's called a point of inflection. Point of inflection, and over here we have a minimum. Okay, so what I like to do for these kind of functions is sometimes, actually let me make some space down here, is to write underneath it, I'm going to write down, make a row, and determine what's happening with the second derivative, or the concavity, and the first derivative, which is whether the function is increasing or decreasing. So up to this red dashed line, we see the function is increasing, so the derivative is positive, and it's increasing. Function is increasing, and it's concave down. So the second derivative is negative, and we have concave down. And in this section right here, it's decreasing, and it's also still concave down. And along here, we're concave up, and the function is still decreasing. So we've gone from concave down to concave up. That's the definition of point of inflection. So we actually have another point of inflection here. Right, and yeah, over here we have concave down. So yeah, that's why we have a point of inflection right there. Concavity changed. It's still decreasing. And now here, let me just draw that back in. Here, between here and here, the function is still decreasing, but it's concave up. So that is also a point of inflection right there. That's the concavity changed. And here we still have concave up, and the function is now increasing. So the concavity didn't change. We went from decreasing to increasing. That means we have a minimum. So that kind of justifies that we have a minimum right there. Next we'll graph the derivative function. So there are three places where the derivative is equal to 0 because the slopes of the tangents at those points is equal to 0. And we have a couple of changes of concavity. I'll get to that in a second. So the derivative is positive here. So it goes down like this. And here we have a point of inflection. So it's going to be, and the derivative is negative in this region, so we're going to have a minimum on our derivative here. And over in this region, the derivative is still negative, so we can't go up here in the positive region. This is, so I should have made it a little bit more curvy. Okay, and this is a point of inflection, so we see a horizontal tangent line here. We have another point of inflection here, so that's going to be a minimum over here. It's going to go like that. Make my dots a bit more pronounced. And here the function starts becoming positive. The derivative starts becoming positive. So it looks like, oops, looks like that. Okay, we'll check our answers with Desmos in a second. Okay, so now that we have that, we know that, okay, for the second derivative, we are concave down and concave down. That means the second derivative is going to be negative all the way up to here. And then it's going to be 0. We're concave up. That means it's going to be positive, and then we're going to have a 0. Then we're concave down, so the second derivative is going to be negative, and then there's a change in concavity, so we're going to have another 0 here. Okay, so this is negative, negative, positive, so it goes like this. Function's negative, then it becomes positive, then it becomes negative, then it becomes positive again. Okay, so if you look closely, the first one is looks like a quintic, and this one looks quartic, and this one looks cubic, which is what you expect when you keep getting the derivatives. So let's take a look at a graph of what this function might look like. And so this is the same function as the original one. And if we look at the derivative, we do indeed get that same W shape. And the second derivative, we do get that cubic shape, just like that. Okay, let's fill out this fill in the blank section now with plus, minus, or well, positive, negative, or 0. At all points where there's a relative maximum, the first derivative is equal to 0, and the second derivative is negative. So second derivative being negative means we're concave down. Okay, so we have this situation, so we're going to have a maximum when it's concave down and the first derivative is equal to 0. And so if we have a relative minimum when the first derivative is 0 and the second derivative is positive, so we have like this situation. So it's obviously a minimum. At all points where y has a point of reflection or point of inflection, the second derivative is equal to 0. Alright, and at all points where y is increasing, y is greater than 0 in our graph right here. Okay, now at all points where y is decreasing, y is less than 0. And at all points where y is concave up, the second derivative is positive. And at all points where y is concave down, the second derivative is negative. Now we have to be a little bit careful about the increasing and decreasing sometimes. Okay, so we need to look at where the derivative is equal to 0 and see if any points are increasing or decreasing there. So if you look at this point of inflection, the derivative is equal to 0, but the function is still decreasing along this whole interval. Okay, so in that case, there is a place where it's decreasing and is equal to 0, so I'm just going to change this to less than or equal to. So be careful, just because, so when the derivative is equal to 0, sometimes it's neither increasing or decreasing, but it could be decreasing or increasing in some cases when we have a point of inflection like this. Okay, next we're going to fill in this table with positive, negative, or equal to 0. Okay, so the function at a is obviously positive, positive, negative, positive, and 0. Actually, this one's right, 0. Okay. Derivative is like the slope of the tangent, so here it would be negative. Here it would be negative. Here it would be 0. Here it is 0, and at e it is negative. And the second derivative, well, that's the concavity. So here we have a point of inflection where the concavity changes, so that's 0. B is also a point of inflection because concave is concave down, then it becomes concave up. So here is 0, or I guess that's the point of inflection. It's hard to tell. And at C we have concave up, so it's positive. At D is concave down, so it's negative. At E it looks like it's still concave down, I think, so it is negative. Okay, next, second derivative test states that the function is concave up at x equals a if the second derivative is 0. And it's a minimum turning point if the first derivative is equal to 0 and we have the second derivative is greater than 0. Okay, and then similarly, it's a maximum turning point if the first derivative equals 0 and the second derivative is less than 0. Okay, so next we'll determine the open interval on which this graph is concave up or down. So we'll need the second derivative. First of all, we can write the function like this, if that helps. So the first derivative equals negative 6 times this to the power of negative 2, chain rule, times 2x. So that equals negative 12 over x squared plus 3 all squared. Okay, so next the second derivative is going to be, we're going to have to use the quotient rule here. We're going to have negative 12x is the derivative, or negative 12 is the derivative of the numerator times the denominator minus the derivative, or we'll do the top times the derivative of the bottom. Derivative of the bottom is this, don't forget the chain rule, all over x squared plus 3 squared. Okay, now so we need to figure out, to get where it's concave up and concave down, we need to first find out where it's the second derivative is equal to 0. So where the second derivative is equal to 0, we just need to consider the numerator. When is that equal to 0? So let's simplify a bit. Let's factor out an x squared plus 3. And inside we're going to get a negative 12 times x squared plus 3. And over here we're going to have negative negative is plus, and this is 2 times 2 times 12 gives me a 48, and x times x gives me an x squared. So we have this. Now notice that x squared plus 3 can never be equal to 0, so we just need to consider this second part, which I'm going to simplify now. So we have negative 12 x squared minus 36 plus 48 x squared. So we'll have 36 x squared minus 36. So we'll have 36 x squared equals 36. X squared equals 1. So x equals positive negative 1 are the points where the second derivative is equal to 0. Okay, so let's set up this little sign diagram. Alright, so we need to look at negative 1 and 1 and what's in between those intervals. Okay, second derivative is 0 at these points. Now if I look at this function here and I plug in a number in between here, let's say 0, then the bottom is positive and the numerator looks like this. Now this one's always positive again, so we just need to look at this part again. Okay, this is like in the numerator. If I plug in 0, I'm going to get 0 here. 3 times this gives me a negative number, and this part is 0. So this gives me a negative number, so in between here you're going to have a negative second derivative, and it's going to be concave down. Now if we take a number like 2, that's bigger than 1. A number like 2, well this is going to be positive, this is always going to be positive. Actually, I'm going to look at this numerator simplified, maybe this quantity. If I plug in a 2 here, you're going to get something that is going to be positive. Okay? And if I plug in a negative 2, same thing. You're going to get something that is going to be bigger than 36 minus 36. You're going to get a positive number. Okay, so here you have concave up, and here you have also concave up. So those 2 points are inflection points, and the question asks just for the open interval on which is concave up and concave down. So we'll say it's concave up on this interval from it's concave up here, here, and here, so that's negative infinity to negative 1 and or union with union with 1 to infinity. Okay, and it's concave down on this interval here, negative 1 to 1. Okay, next we're going to look at this graph. It's only defined from negative 3 to 3. For what values of x do we have a relative maximum and a relative minimum? Now be careful, this is the graph of, maybe you can't see that well, this is the derivative, not the original function. So at a maximum minimum, we'd expect the derivatives to be 0, so we need to look at these points are where the derivative is equal to 0. And here we have the derivative is positive, and then we have the derivative is negative. So the derivative is positive, then the original function is increasing, and then it's decreasing. Okay, it's increasing, then it's decreasing. So this is obviously a maximum. Yeah? So we have a maximum at x equals negative 2. Now over here we have the derivative is negative and then it's positive. So it goes from decreasing to increasing. Okay, so we have a minimum here at x equals 0. Now here the derivative is positive and the derivative is still positive. So it goes from positive to positive. So at x equals 2, we actually have a point of inflection. It's not a minimum or a maximum. Right. So part B, for what values of x is f concave up? So it's concave up when the second derivative is greater than 0 or positive. Okay, that means the slope of the first derivative tangents would have to be positive, right? So let's look at the slope of this graph. Here is negative, negative. Here we start to have some positive slopes of tangent lines. Yeah? There's a positive slope. So from here to here, the slopes of the tangents are positive. So I would say from negative 1 to 1, and over here, slopes of the tangents are positive. So 2 all the way up to 3. Where concave will be concave up as well. Okay, hence, sketch a possible graph of the function given that f of negative 3 equals 0. Okay, so let's draw it right underneath here. I'm going to try to get about the same scale. 1, 2, 3. Alright, so let's do this underneath here maybe. Derivative and second derivative. Okay, so we said it's concave up from negative 1 to 1 is concave up. And from 2 to 3 is concave up, so everywhere else is concave down. And what else? We have the derivatives are positive, negative, negative, positive, positive, positive. And we have f of negative 3 equals 0. So let's draw that in red. Okay, then the function's increasing and concave down. Okay, and we're still concave down, but now the function is decreasing. So I'm going to go down. Okay, we're still decreasing at this point, but it's going to go to concave up. So I'm going to go like that. And we're still concave up, but the function is increasing, so I'm going to go like that. We're concave down, but the function is increasing, so that's like a point of inflection. And here we're concave up, and we're changing to concave up, and we're still increasing, so that's another point of inflection. So it looks like that. So we have a lot of points of inflections, yeah? There was a point of inflection, another point of inflection. Alright, next we're going to look at this one. Point of inflection is a point where the concavity changes. To test if there's a point of inflection, you must find where second derivative is equal to 0 and test points near where second derivative is equal to 0 to see if there's a change in concavity. Okay, so let's look at this first example, which is actually just a graphical example. Here's the function. They give us the function, so we're going to find this inflection point here. So we'll need to find the derivative, which equals 3x squared minus 18x. And the second derivative is going to be 6x minus 18. Alright, so we're going to, in order to find a possible inflection point, let's set the second derivative equal to 0, and we get x equals 3. Alright, so that point is x equals 3. We could check to the left and right. We'll get a, this is concave down, so you get a negative second derivative. Here you get a positive second derivative. So you clearly see that this one here is going to be a point of inflection. Okay, now be careful. Be careful for y equals x to the power 4. So I'll show you why now in a second. So f prime of x equals 4x cubed. Second derivative equals 12x squared. So when the second derivative is equal to 0, we have x equals 0. So if we check that, add x equals 0, and check the second derivative. So we plug in a 1 to the second derivative, we get a positive number. Put in a negative number, we get a positive number. So there's no change of concavity. Okay, and actually the graph of y equals x to the power 4 looks like a big fat parabola, and you see it's concave up for the whole thing. So remember, to test it, you also have to not just find where the second derivative is equal to 0, you also have to test to the left and to the right to figure out if there's a change in concavity. Okay, next, function y equals f of x has these characteristics. Alright, so f of 3 equals 5. The derivative equals 0. So maybe we have a maximum or a minimum. But the second derivative is greater than 0, so that means it's concave up at that point. So we actually have a minimum because of that. Okay. Next, in this situation, f of 3 equals 5. Second derivative is equal to 0. But the point of inflection is also equal to 0. So the only way to figure out if there's a point of inflection is to test to the left and to the right of this point. So we can't really tell in this situation. Okay, next, sketch the graph of the function with these characteristics. Okay, so we have a couple of points. F of 2 equals f of 4 equals 0. So that means that red. F of 3 is undefined. That could mean could mean a hole or something, but it might mean an asymptote, so I'll go ahead and draw that in there for now. And the derivative is less than 0 when x is less than 3. Let me put that on the bottom. The derivative is less than 0 when x is less than 3. So that means over here the function is decreasing. The derivative at 3 doesn't exist, which you would expect with an asymptote. The derivative is greater than 0 when x is greater than 3, so it's increasing over here. And the second derivative is less than 0, basically for all x except for 3. So the concavity is always down. Okay, so it's always concave down, and we have enough information to make a sketch right now. Okay, the function is decreasing and concave down for this whole section. So it has to look like this. Okay, and it goes off like this. Yeah, it never goes this way because it's concave down and decreasing for the entire function over here. Okay, and over here it's increasing and concave down, so it'll look like this. Okay, next show that the point of inflection for this function lies midway between the relative extrema of f. Okay, so let's actually find the maximums and minimums first. So let's look at it. Let's expand this first. So this is x times x squared minus 12x plus 36, which equals x cubed minus 12x squared plus 36x. And the first derivative is 3x squared minus 24x plus 36. So when that is equal to 0, we have, well, I'm going to divide everything by 3. We have x squared minus 8x plus 12 equals 0. Solve that, we get this. So x equals 2 and 6 are the critical values. So let's figure out if we have maximums or minimums there. Okay, f prime of x, 2 and 6, and the derivative is 0 at those points. Now in between 2 and 6 we have a number like 4. Plug 4 into the equation. Let's look at this part here. We plug 4 in here, we get negative times positive is negative. If we plug in something like 7, we'll get positive, positive, positive. And something like 3, this will be negative, this will be positive. Actually, sorry, to the left of 2 we have a number like 0. If we plug in 0, we'll get a positive number. Anyway, so we have increasing to decreasing. So we have a maximum, then we have decreasing to increasing. So we have a minimum here. So this is a max, and this is a min. Those are the x values of the maximum and the minimum. Alright, we'll need the y values because we're talking about the midpoint of these 2 points. So we have 2 comma and 6 comma. Let's just get the y values. So let's plug it into the original equation. If x is 2, we'll have 2 minus 4 is negative 4 squared is 16 times 2, and we get 2 comma 32. And if x is 6, we actually get 0. Okay, so those are our 2 points, 6, 32. Those are our 2 extrema. And let's get the midpoint, and then we'll check the second derivative. So the midpoint is 2 plus 6 over 2, the average of the x values and the average of the y values. So this gives me 4, and this gives me 16. Okay, so we got 4, 16, and so we're going to check now the point of inflection. So we're going to get the second derivative. So second derivative of that equals 6x minus 24. We'll set that equal to 0, and we get x equals 3. sorry, x equals 4. So here's 4. Let's check out the second derivative. A number bigger than 4, like 5, will give you a positive number, positive second derivative. Less than 4 will give you a negative second derivative. So the concavity changes, so we do have a point of inflection. And x value is 4. Plug that in. 4 minus 6 is 2 squared is 4. 4 times 4 is 16, which is what we got for the midpoint. So they are indeed the same. Okay, next we have some true or false questions. The graph of every cubic polynomial has precisely, so it should be 1 point of inflection. That is true. Okay, you can prove it by looking at a general polynomial, a general cubic, ax cubed plus bx squared plus cx plus d, and then find the derivative, and we get 3ax squared plus 2bx plus c, second derivative, 6ax plus 2b. Now when that's equal to 0, we get 0 equals 6ax plus 2b, and we get x equals negative 2b over 6a, or negative b over 3a. Okay, so we get one possible point of inflection. So let's set up the sign diagram. Now if you have a bigger value of x, you're going to get a positive second derivative. If you get a smaller value of x, you're going to get a negative second derivative. So we do have a change of concavity, and you have an inflection point for every cubic. Let's look at b. Graph of 1 over x, looks like that, right? Is concave downward, concave upward, therefore is a point of inflection. Well, no, because it's not defined at that point. Okay, so if it's not defined at that point, we cannot have a point of inflection. There's not even a point there. Next, if f, the first derivative is greater than 0, the function is concave up. If the first derivative is greater than 0, then the function is concave up. That is false. If the second derivative is greater than 0, then the function is concave up. So that is false. Maybe you could show an example of a function that the derivative is positive but it's not concave up. So just like maybe the square root function. Yeah, it's never concave up and it's always got a positive derivative. So part D, second derivative is equal to 0, then it must have an inflection point. Well, no, and we have examples of functions like that, like we saw y equals x to the power 4, right? That function has a second derivative is equal to 0 here, but it's not a point of inflection. So we cannot determine if it's a point of inflection just by looking at where the second derivative is equal to 0.